Hello, my name is Vincent Wagner, and I'm happy to present the poster about Eulerian parameter inference. This novel type of variational or probabilistic inference is especially suited if you're having heterogeneous data that you want to explain using a simulation model. And for this example, we start at our data set, which is depicted here on the top left. What you see here are annual average temperatures, YI, of many cities around the globe. And we would like now to explain these data points using a simulation model. In this very basic example, which is relatively academic, we have this algebraic equation where 60 times the cosine of my latitudinal coordinate qy minus 30 should equal the annual average temperature. Now, of course, ideally, we would take these data points and invert the simulation model to get qi out of inverted simulation model applied to the data point. However, it's not really easy in general to do this. Of course, for this very simple model, you could do this, but in general, it's not possible. So we propose to take a small detour to solve that problem very elegantly and still very efficiently. And what we do in the first step is we estimate the density of these data points. We basically assume that these heterogeneous data points come from an underlying data distribution, and we would like to estimate the density of this distribution. We use kernel density estimation in our setting here, and what we get is this distribution of temperature, of average annual temperatures of all our cities. Now comes the fancy part. In the space of distributions here, we can now use a random variable transformation to back transform our data distribution into our parameter distribution using this equation depicted here at the bottom. And the magic part about this is that you can get one evaluation of your parameter density by just taking one simulation output S of Q, plugging it into your data density phi y, and multiplying it with the sensitivity of the model with respect to Q. From this density here, we can of course sample to get then our latitudinal coordinate that corresponds to these data. Now, of course, it's easy to say that, but how do we know that we're right? Well, easy. We take our simulation model and our inferred latitude parameters, and we just put it into the forward simulation to see how our prediction aligns with the data. And what you see here, if you now compare the density estimation of our inferred parameters and the original data, you see that they perfectly, really nicely overlay. So to summarize, we have two very strong points here. First of all, we can solve this inverse problem of getting our parameter distribution from our data distribution only using forward simulations. We only use forward simulations and their derivatives. There's no single inversion needed. We can use a pointwise evaluation of the inverse problem, and we can just calculate it. And secondly, without defining any likelihood as you would do it in a Bayesian setting or any distance function as you would do it in an approximate Bayesian setting, we perfectly reproduce our data distribution here. Besides, just as a small nice aspect, if you compare the true distribution of our city latitude coordinates of these data points to what we inferred, we even see that our model does quite a nice job. So in this case, even modeling error plus approximation error is very small. And with this, I would really like to to get your attention, check out our QR codes. You can get the tutorial of our method here at the bottom right, and you can have a look at our GitHub at the bottom left. It's a very strong toolbox that you can get here, and if you have an SBML model, we have SBML support in our toolbox. We can support basically any differentiable and non-stochastic model here, and we would be happy if anybody of you uses it for his or her research. Thank you very much, and have a great conference.